This final project is looking at an unknown ester through MS-IR, H-NMR, and C13-NMR, which are the 4 spectra that we have learned about in our organic lab this year. This project is by Haley Hollinshead, Hannah Roberts, and Caitlin Rosner.
So beginning with mass spectrometry, our M+ peak is 152. As you can see right here, the M+ peak also represents the mass of the compound. And then next up we'll do the base peak, which is the highest peak on the mass spectra. And here it's represented as 121. And then using the M+ peak and the base peak, we can then find fragmentation patterns. And subtracting 152 minus 121, we get 31. And so M minus 31 will be our fragmentation pattern. After that, we can do our degree of unsaturation using this equation up here, which is 2C plus 2 plus the number of nitrogens minus halogens minus hydrogens, and all of that over 2. So using the numbers from the equation we're given, which is C8H8O3, we get 2 times 8 plus 2 plus 0 because there's no nitrogen, minus 0 because there's no halogens, and then minus 8, and then all of that over 2, which ends up giving us 5 for a degree of unsaturation, which would mean we could have 5 different combinations of rings, double bonds, or triple bonds. And then our last step is determining whether there would be any other halogens or anything present in this compound. And since we already know that it's C8H8O3, there is no bromine, iodine, or chlorine, so no halogens present.
We use this graph within IR because we can line up our graph and see what structures line up with our peaks and maybe use this to help build our structure. So next we have the IR graph, and when we're looking at the IR graph, we're looking into 5 different zones. So in the first zone, which is about here, we're looking for things like alcohols. They have like a tongue shape. There's primary amines. They have vampire fangs, we call them. There's a 2-amine or a terminal alkene, which is just like 1V, and then there's a carboxylic acid, which resembles a beard essentially. So here you can see we have an aromatic. So that means it's going to be like a benzene ring. And then in the next zone, we're looking for like CH bonds, sp3s, aldehydes, carboxylic acids, and in here you can see that we do not have anything within this region. So there's nothing present within this zone. In the next one, we're looking for triple bonds either from C triple bond C or C triple bond to an N. Once again, you can see that there's nothing there, so we have no bonds present. In the next zone, we're looking for carbonyls, ketones, so like a C double bonded to an O. In our zone, you can see that we do have a C double bonded to an O present. And then finally in the last zone, we're looking for like alkenes and benzenes, and you can see all in here we have all these different spikes. So we most likely have a C double bond to a C or a benzene ring. And now once we have all that.
So now we're going to be looking at this formula with proton NMR. And the first thing we notice would be how many peaks we have shown on the spectra. So here we notice we have 1, and because it is a single peak with no splitting, we know according to the N+1 rule that it has 0 hydrogen neighbors, this one proton here, according to the integration number as well. Here, for this peak, we see that the integration number is 3, which means that we have a CH3 group because we have 3 protons, and because it is one strong peak, we know according to the N+1 rule, we have 0 neighboring protons. So if we move over here to our last section that we are going to analyze, we see that the integration number is 4, which means that we have 4 hydrogens, and because of all this splitting in the pattern, we can tell that they are very close together. And with this pattern, we are also aware that it is not going to be para, like the way the groups are attached onto the benzene ring. And this is because we recognize that this pattern doesn't match the one we learned in class. So it's either going to be ortho or meta. So now if we're looking at whether we have triplets, quartets, things of that nature, we can see that we have a single strong peak here, which means that this is a singlet, a single strong peak here, which is a singlet. Here we have a doublet, here we have a triplet, and here we have a quartet. Finally, the last thing that we analyze in proton NMR is according to the downfield shift in the spectra where these signals appear. And so the more downfield shifted they are, the closer they are to an electronegative atom, such as the oxygen we have in our formula. This also means that the closer the protons are to the electronegative atom, the more deshielded they are. So according to our MR, IR, and proton NMR, this is the structure we came up with that fits the requirements found in the spectra. So as we can see here, we have one proton with no neighbors, which can be found here off of the alcohol. We have 4 protons that are close together, which are going to be the 4 on our ring here. 4. And then we have 3 protons that have no neighbors, which can be located right here in the structure. And the structure we drew for this is methyl salicylate. This structure also fits the DOU that we calculated in the beginning, which was 5. So we see that we have 3 pi bonds, 1 ring, and then 1 double bond. So that adds up to 5. We also see that we have the ester that we found in our initial IR analysis, and the C double bond to C up here, as well as the aromatic that we predicted that was going to be in the structure.
So here we use this graph to figure out where on this chart the carbons within the structure line up here. So here we can see the first carbon surrounded by 3 H's and an O is at this point here. And this is because a C bonded to an O has a range of about 0 to 50, and that falls right into that range. The second, third, and fourth, which are all tightly packed here between the 100 and 120, are there because a C double bonded to another C has a range of about 100 to 150, and these 3 are our 3 double bonded carbons. The 5 and 6 peaks are C bonded to another C in an aromatic ring, which you see here and here, fall between the 125 and the 150 range. The 7 out here lines up with our OH, and this is because a C double bonded to an O bonded to an H has a range of about 150 to 200. And then finally, our C double bonded to our O here has a range of about 150 to 200, and so that's why those fall there. So we use these carbon environments to figure out what functional group belongs where. So you can see here that the farthest one down would be our functional group here, which is an ester.
This has been our final group project for the first semester of Organic Laboratory, and we would like to thank you for watching our video.